So hi, today I'm going to recount how I converted this cheap nasty power supply from China into a pretty useful variable current source. Keep watching. I did do a previous video in which I reviewed this, and I'll link that in down below. But as well as doing the conversion into a variable current source, I also need to deal with the following problems that I found. It's not earthed, it's got exposed live connectors inside, there's some really poor soldering onto the main board of the mains connections. There are cables flapping all over the place, and I'm talking about mains cables, not low voltage. It's got actually quite poor regulation. So for example, on the video you're just looking at, you'll see that there are 30 volts set, and it appears to be delivering 30 volts, but it's actually 200 millivolts out, and that's 40 millivolts error per amp, and the meter is reporting what it thinks it's regulating instead of what it is regulating. There are other problems. There's no on-off switch for the output power, and you can't actually set a current limit or preset the voltage and then turn the output on. In fact, the current limit is completely pointless, because since you can't set it to a known value, what's the point of it? Anyway, so just got to fix all of that as well as converting this into a variable current source. Let's get started with an overview of the mod. So I'm just going to start by looking at the existing power supply, because we're going to want to reuse most of this in our design. Certainly this contains all the high voltage, high current stuff that we don't want to be redeveloping. Essentially the two boards, there's a main board which has got the voltage control and the current control on it, and we've got the display which just displays whatever's on the output at the moment. So our voltage set is a pot, and it applies some voltage to the main board, which represents the output voltage we would like on the output. So let's say that is 0 to 30, and we like 0 to 30 on the output. So, and we set it to 10. So vSense looks at that 10, and it looks at what's on the output, and if the output is only 9, let's say, and it's a bit too low, it will push the output voltage up a bit, and it will continue to push it up a bit until it equals 10. Similarly, if it's too high, if it's say 12, then it will pull that output down a bit again until it equals 10, and it does that constantly, very, very fast, and therefore keeps the output exactly where we want it, and it will do that irrespective of how much current the load draws. Now if this weren't regulated, then as we drew more current, then the voltage would sag. Now one of the implications of that is that, you know, we're delivering our, let's say, 10 volts, and this device that we've got it plugged into is drawing a lot of current. It may be too much current. So we have, as a secondary function, a current limit, and that actually does a very similar thing. Instead of sensing the voltage on the output, it senses how much current is on the output, and it basically has a little resistor in series with the output, and it measures the voltage across that resistor using Ohm's law. We can calculate the current. So we set some voltage that represents the current limit. We measure the voltage across our shunt resistor, which is our current sense resistor. We compare the two, and if the amount of current being drawn is too high, we can't regulate the current independent of the voltage. So what we do is we drop the voltage. So essentially the iSense communicates into the voltage output circuit and causes the voltage output to collapse, to keep the amount of current being drawn within the limit. So here's my initial thoughts. So the first job is to take the main power supply board and simply link up the current limit to maximum. That's so that the mod board can actually manage the current anywhere between 0 and the maximum level. So that's easy, and we just need to find out what voltage it is, and we pin that input to that voltage, and that's job done for that one. The next thing we need to do is to actually steer the voltage of the power supply. So the principle here is that we have some load, and at a given voltage it will draw a given current. Or it will draw a given current, and it needs a certain voltage in order to do it. We are going to give it exactly that voltage so that it gets the right current. So here's our new little box on the left hand side, and we can see it's joining into the existing power supply in a couple of places. So the first is it's pinching the current sense, because we're going to need that is for certain, and it's replacing the pot that was going to set the voltage with its own output. And that's kind of about it as far as the main board is concerned. So our circuit is what? Well, we set our desired current. So instead of setting our current limit, we set the current we would like to be outputting. And we have a comparator. And what we're going to do is we're going to compare the actual current that we're outputting that's sensed over here on the main board, and we're going to compare that against the current that we are actually outputting. Now if that current is too low, then we will essentially steer the voltage of the power supply upwards. So by steering the voltage upwards, we would cause the load to draw more current, because that's Ohm's law, and kind of how that works really. So that's fairly straightforward. Current too low, we steer the voltage upwards until it is drawing the right amount of current, or sourcing the right amount of current, I should perhaps say. If the current is too high that's going out that output plug, then actually we lower the voltage a bit until the current is correct again, and we do that on a constant basis. So that's exactly the same as the original was doing with voltage, except we're doing it in fact it's exactly the same as doing with voltage, but instead of sensing and driving the voltage off the voltage being output, we're sensing and driving the voltage off the current being output. So we just change the control around really. Now a downside to that, of course, is that something may want to draw a fair bit of current, and in order to do so it needs a huge voltage, so it's going to just shove that voltage up through the roof, and that might not be desirable. That might destroy the device that we are plugging in. So we want to be able to limit the voltage that we're outputting, and we do that with vlimit. And actually I will pinch the two existing pots and just repurpose them for this. So vset on the existing is a multi-turn pot. I'll put that down for the current set because that's where I want the precision, and current limit is a simple pot on the original, and I will reuse that for the voltage set. So again, this is really just a comparator, and essentially actually it's a clamp, and essentially we have an input voltage coming in from this side, and should the voltage that we're attempting to steer to be higher than that, then we clamp it to that limit. So this works a little bit different than the original current limit, which caused the voltage to collapse. Essentially with the clamping mechanism we will stop increasing the voltage at some point, and that just means that the current might not actually reach what we want, but it will still be outputting something. So it's a little bit less drastic than the way the current limit worked before. So that's it. That's the mod. Now let's just switch on to the next page and look at that in a bit more detail, because there are a couple of other things I said I wanted to do. So it's not very good if we can't sort of preset our voltage limit and preset our current and then turn our output on and then measure the current going out. So these three switches here are doing that. So this one here is switching the output on and off. This one is happening in concert, and what I've done is I've moved the voltage detection for the display across onto the actual output itself. So just before the switch and just after the switch basically, so that we get a very accurate reading of what the voltage is on the actual output socket. If we open this up then actually and switch our switch down to the lower position, then actually it's monitoring a voltage that should be being presented but isn't. And what is it monitoring? Well, it's actually monitoring the V limit, and the reason for that is that the output current, once we open that switch, becomes 0, and as a result our mod drives the voltage all the way up until it's clamped by V limit. So the power supply attempts to output the voltage limit, and we can measure it and display it on our little display. So that's brilliant. So that solves that problem. In fact, we don't even really need this second switch up here, because we could just connect it directly on the start here. Now there would be then a tiny bit of loss, tiny bit of voltage drop across that switch. So it's not quite as accurate, but in practice I might have to do that because there's not enough room in the box for very much. And we've got a similar switch up here, and you'll see that I've changed the iSense line and it's coming off the display now. Now the reason for that is the sensor on the board is only developing about 0.1 volts, and that represents 5 amps. So that means we're talking microvolts per milliamp on the setting, and I don't really want to be down in there. I'm going to have noise problems and all sorts of stuff, but it amplifies that up so that it can digitally sample it. So what I've decided to do is to take my current sense from the output of that little amplifier that's on the display board and feed that across to the mod instead. And that's really helpful because that gives me a better range for the iSet pot, and also means I can just put a switch in there and my display can either display the current that we've got set on my pot or the current that's actually being output. Well, it's displaying the voltage that's equivalent to those, of course. So again, that gives us a preview of the current set point and the voltage limit point when I open these switches, and I'll join all these switches together so they work in tandem. So literally just turn off the output and we get our current set point and our voltage maximum limit, and then close this and it measures the actual output current and actual output voltage. In order that I can finish my design, I need to measure a few things. So for example, the range of the current sense shunt, the range of the amplifier output, which I'm probing at the moment on the display board, and just trying to hold the probes, and altering the amount of current it's drawing and seeing what the actual range of output is and how it alters. So there we go, we can see I'm just turning up the current and the voltage on that output of that amplifier is changing correspondingly until I reach the limit of 1.472 volts. So I now know the range of my current set has to match that 1.472 volts. And I'm going to go around and probe a lot of other things. Obviously the voltages on each of the input sockets. On the display board, I'm expecting to find my power supply for my board on there. I need a split mode power supply, so I need plus 12, minus 12 and 0 volts, something like that. It might be bigger, smaller, don't really care, as long as it will power up my op amps. I'm expecting to find of course a voltage input on there for it to be displaying the voltage as well. And yeah, I'm just going to need to decide also where to cut into this board so that I can intercept the current for displaying whichever I choose, the set point or the actual current. Yeah, so I think that board will have everything that I want on it, and of course I do also need just to test the voltage ranges of each of the pots, and my my negative is actually plugged into the voltage pot at the moment, just borrowing its ground connection. Okay, let's take a quick look at what I found. So voltage control, I found unfortunately that the pot outputs a inverse relationship with the output. So at 0.29 volts it outputs 30 volts, and at 4.53 it outputs 0 volts. So that's a little awkward. And then we've got the outputs from the amplifier for the current, and we can see that ranges from pretty much 0 volts all the way up to 1.4715, which represents 5 amps. So that's handy. That is a linear relationship and not inverted. And we've got some suitable power supply on there as well, although it looks a little bit lower than I would like. It's not quite 8 volts. So anyway, there we go. We deal with what we've got. So I was planning to build this on a big piece of board that would fit down one side of the case, but space is limited, and I thought I'd have a go at doing a piggyback board on the back of the display. Not 100% sure it'll work, but I can actually mount the two boards together with some connector pins. So at least initially it looks pretty neat and tidy, but space is limited. Anyway, here's the circuit we're going to build, and this deals with a few things. Now there's a second page to this, and on the left hand side I've got an analysis trace which I will cover in a second or two. So first up we have got our current sense, and that is this whole section just here, and we could include this section here as well, I suppose, but you know, it's there. So on this input labelled iSense amp, then we've got what is supposed to be the input sense happening. And I've got a little ramp generator, or staircase generator, which is simulating choosing different currents that we would like on the output. And on the simulation, that is a little blue staircase going up from 0 up to, what is it going up to? 1.462 volts. So pretty much representing a full range of current going in. Now we need to compare that to a set point, and we get the set point by first of all using a 5.1 volt Zener to create a stable reference voltage. And why am I doing that? Well, because it turns out that the positive and negative rails that are coming off that board don't appear to be regulated. So although I'm setting them at 8.2 volts, they might be as low as 7 volts. So I need to put a little bit of regulation in. I know Zener does the job perfectly adequately. So we get 5.1 volts, and that goes through. It's got a 27k ranging resistor, which means that this 10-turn pot here, which is a 10k pot, it can choose between 0 and 1.472 volts. And it's kind of that simple. I mean, there'll be a tiny bit of error in there because it's 27k versus 10k and 5.1 volts, but it's within a percent or two of what we need. And since we actually turn this and we read the value on a display, it doesn't really matter if there's a tiny bit of inaccuracy there because that goes away. And they go into both sides of an op-amp, and this is a JFET input, an LF351, and this is not an ideal op-amp for this job. It's just what I've got in the drawer. I had an OP97, which I thought would do better, but the problem is it draws actually a surprising amount of current in on this input wire. Let me click away from that so I can pick the wire. So in this input wire from the pot, it draws a surprising amount of current and causes the voltage to drop down. So yeah, and also it doesn't isolate very well between these two inputs. So yeah, not as good as I thought. So I went for a JFET input op amp because it has really high input impedance, and these become very independent. Now, if I was building this commercially, I would actually put a buffer amplifier on the output from the pot. And probably also from the iSense amp to fully isolate this circuit from everything else. But you know, I just want to fit this on 4 square inches of perfboard and use as few op amps as I possibly get away with. So I haven't modeled the output there, but essentially we can see that the set point on this diagram here, where it is switching very strongly from 0 volt through to its maximum voltage that it can output. And then this is a pair of resistors here that forms a voltage divider just to scale that, because I don't want 5 volts or 8 volts or whatever that op amp will provide. I actually want 4.56 volts as my maximum. Now there's a problem then, because in theory we would take this and we would just scale its output and use it to drive the voltage, but this is bipolar, so it can actually go negative. And secondly, there's another problem with it, which is and if I made it so it's just on the positive rail, then it wouldn't be able to reach 0 volts, so that's no use. So I have to have it bipolar. That means it can go negative. I don't want it to do that. I want it to stop at 0 volts. Also, on the other side, I want it to stop at 4.56 volts. But the problem is it has to be inverse. So when I want 0 volts output, I need it to have 4.56 volts. And this is what essentially this section here is doing. Now, those who use op amps a lot might recognize that this is in actual fact a half-wave rectifier. So it's a so-called perfect half-wave rectifier, in so much as it goes all the way down to 0 volts. So we don't have the typical forward voltage loss that we get in the diodes. So if you just put a diode in here, that would get rid of all the negative voltages, no doubt about it. But unfortunately, it wouldn't actually turn on until you got to 0.7 volts. And that's not ideal. We could probably actually get away with it in this circuit because we've got feedback going all the way back to this operation amplifier here, so it could compensate out that diode, potentially, provided that we give it enough voltage range in which to do it. But life starts getting very complicated when we start doing that sort of stuff. So this is simple. So we scale this input here so that it can go between plus and minus 4.56 volts. That goes into this guy here, which is the rectifier, which is going to get rid of the negative half. And conveniently, it will invert the input signal. So this solves our problem of making it come down from 4.56 volts, which will represent 0 volts out, down to 0 volts, which will represent 30 or 32 volts out. So yeah, so it's quite a handy little circuit there, and that is essentially setting our lower limit. So what I mean by that is this actually sets the maximum that the output steering voltage can go, which in turn sets the lowest that the voltage can go, which obviously we wish to be 0 volts. Okay, so we've got that. That's absolutely great. Well, now what we need to do is we need to limit it. So if we look on this graph here, we can see this red line, and we can see it's kind of switching fairly rapidly in the center. So it goes along at 0 volts, and then when the current reaches the current sensed on this staircase that we're simulating the current output from the device, when that reaches a certain level, we need actually to start lowering the voltage. And what happens here is that the opamp therefore raises its voltage from 0, its output from 0, and pushes it up to 4.332 in the simulation. So that's absolutely fine. Now I need that to be a little bit higher, so we could alter these resistors. Now in the circuit, I will actually replace these with a 10K trimmer, so I can trim in the exact voltage that I need on this op-amp, so it can go accurately between its two reference points. Okay, but anyway, that red line shows that it switches between 0 and maximum volts. I say switches, it slews between the two. It's not instantaneous, but it's pretty fast. And of course, it's receiving feedback, which is going to moderate that slew when it reaches the right voltage. So all we need to do now basically is stop it going all the way down to 0, because 0 is 32 volts. And you know, that's not where we want to go all the time. We want to have a variable amount, a variable limit. And here is our clamp circuit. So this is a circuit you should have in your little notebook if you haven't got it. And you can also put another op-amp on to do an upper clamp as well. But essentially we want to stop our output from our device, from our mod, going into the power supply from going too low, because too low on our output means too high on the actual power supply itself. So we've got the same that we saw before. We've got our little Zener creating a reference voltage, and we've got a pot with a little series resistor limiting its range, so that we can dial in somewhere between about 0 and 4.6 volts, thereabouts. And that will actually set our lower limit, below which the output voltage may not fall. So if the steering voltage coming in from the previous piece of circuitry drops below whatever voltage we've set, and on our simulation at the moment it's set to 2.29, something like that, 2.3 volts. If it drops below that, then it will clip and hold at 2.3 volts, and you can see that on the simulation graph on the left hand side. The red line is the voltage steering requesting 0 volts, and the voltage output going to the power supply control circuit is actually limiting at 2.3 volts, thereabouts. And if I change the extent to which the pot is turned to, let's say, 80%, then we can see that it clips at a much higher voltage. So this is our so this op-amp here and this op-amp here form our clamping circuit, and you can see that literally it's just 2 op-amps and 2 diodes back to back. And these are LM385 pair of diodes in one package. And that's it. That's all we need to build. Now we'll need to pop a couple of capacitors on and things like that to decouple the op-amps and what have you. and we'll need to just double check all these values when we actually get the real parts. But yeah, we're basically done. Okay, so at this point the build is pretty much done, just about fitted on the board. A couple more connectors to put on, and I'm just going to test this out now and make sure I've made no gross mistakes in terms of short circuits or anything like that. So just going to buzz it out and check a few voltages, check a few levels, gradually connect it up before I put the op amps in, and just make sure I haven't done anything really stupid, and then I'll connect it up to the main circuit board and we should be up and running. And I'm pretty much up and running with everything, just adding the op amps one at a time, checking the various voltages, making the adjustments needed, and just generally setting everything up. Yeah, we can see the voltage has dropped just a little bit on the supply rail, so not regulated as I suspected, and actually that could cause me a few problems. Okay guys, so here it is up and running. We can see here that it's outputting 13.8 volts at 140 milliamps, which is absolutely fine, and on here it's 138.7, so that's a perfectly acceptable measurement. And over here we've got 13.84 as the actual voltage that is actually being output on those pins. So happy with that, that's behaving itself quite nicely. Now, what's different about that, you may ask? Well, the answer is that I can turn the voltage up as much as we want. And we're just getting to what, 14.8 volts, 15. Why is that? Well, because I asked for 0.15 amps. So it's got an on-off switch down here now. I can switch that off, and this is now the set point. So I've said it may not exceed 32 volts. It must regulate at 0.15 amps. That again. Thank you. And when I turn that on, I get my 150 milliamps thereabouts. I get my 14.8 volts, which is what is necessary to drive the particular load I've got load on it at the moment to 0.15 amps. So yeah, so actually this is regulating current now. I can change the current, there you go, and you can see that the voltage changes with it in order to deliver the current. So if I turn this up, let's turn it down a bit further than that. So there you go. 280 milliamps requires, I've got 100 ohm load on this, and here's 278, and I'll talk about the slight difference in a second, not so much between that reading, but between the set point. So I've asked for 0.3 on the set point. I'm actually delivering 0.28. So that is to do with the fact that I had to swap out I was using an OPA 97 for my input comparator, which is very accurate, but it turned out it got some other problems relating to current draw on the inputs, which was causing all sorts of difficulties for me. So in the end, rather than messing around trying to make that work, I dropped that out and just stuffed in an LF351 that I got in the drawer. But that is it's a magnitude worse in terms of its offset voltage. And that reflects onto the set point versus the actual point. Although, you know, it's not really worth worrying about in this type of class of equipment. But anyway, so there you can see we're getting our 0.28 amps, which we're requesting, and it's delivering 27.8 volts in order to do so, which matches up very nicely with these two readings here. Now, if I turn the current up, if you remember, I've got a 32 volt limit. So there we go, 32, 320 milliamps being delivered at 32 volts. Let's try and go further. Nope, forget it. Can't go any further than that. So let's turn up the resistance. Let's turn down the resistance to 25 ohms. I have to turn it on. And now we can see I've got my 0.33 amps that I was asking for at 8.1 volts. And of course I can continue to increase my current now. So there's 1 amp, 1 amp. So yeah, so there we go. There it is, regulating its current, and the voltage is following along and is correctly limited. So I can set, there we go. Let's turn that off for just a second. So let's set my voltage limit to 25 volts. I'm asking for 0.8 amps. Let's turn it on. So 19.7 at 0.79 amps. Just turn it up. And there we go. We've actually got 1 amp being delivered at 2.49. But let's look what I'm asking for. I'm actually asking for 1.81 amps. And oh yeah, I've drifted to 24.9 as my limit. So there we go. Voltage limit works, current regulation works, on-off switch works, presets work, in fact everything works. Okay, so here it is. I've turned it sideways so we can just see inside, talk about a couple of things. So up here we've got a new earth connection properly made onto the chassis. It now passes its safety tests. I've insulated the connections onto the IEC connector down at the bottom, so that's all a lot safer now, and I've redone all the connections on the back of the board, so they're properly anchored, and some cable ties and things like that just to hold things in place. So that's all a lot safer than it was. Obviously we've got an on-off switch for the power. It's not just for the power but for the outputs now, and we can use a set point, so that's all great. The board itself was intended to go on the back of the display panel inside here, but I kind of underestimated the effect of some of these sockets and things on it, and yeah, I needed just another couple of millimeters of space, and I didn't really want to shuffle this board any further to the back. I think it's kind of pressed up hard enough against the wires on the fan and stuff. So I decided instead that I'm going to mount it just here, which strangely enough is where I originally intended to mount it. Improvements to the circuit. I'd originally intended on, you can see I've got various notes written across here. Some of them are just layouts of op amps and the boards as I've done it. So on here I'd intended, this is the comparator circuit, which actually manages the accuracy of the set point versus the actual current. And I'd intended to use an OP97 on there, and I tried that and had a lot of trouble with it actually drawing too much current through the iSense line and the iSet line, the pot, and yeah, so it wasn't actually regulating properly because of that. So I didn't want to do any more with that. The reason I chose the OP97 was because of its accuracy, its input offset accuracy. But once you start getting current flowing through, then that all goes to pot, to be perfectly honest. So I just replaced that with something else I got in the drawer, which was an LF351. Now this has got 25 microamps, so microvolts of offset. Unfortunately, the LF351 is 3 millivolts, and unfortunately, it's something like 100 microvolts per milliamp error on here. So yeah, there's a fair bit of error introduced by changing that. Yeah, I've changed that to an LF351 as well, just to keep. The reason I chose LF351 is because it has really high input impedance, so I don't have to worry about the effect of the op amp on the preceding circuit, essentially. And that's behaving itself fine, I think. It reaches the voltages that I'm expecting, etc. on its rails. Here we've got the voltage limiter, and we do have a problem with this. So this is an LM358 dual op amp, and this is clamping before it hits the rails, unfortunately. It's clamping too far from the rails, I should say. So the problem is the rails are about half a volt lower than I thought, because they're really, really weak. So as soon as you power these op amps, they actually drop off a little bit, unfortunately. So I've only got about 7.4 volts or so, and I've got voltage drop on these diodes, and I can't get close enough to the rails with the op amp that I've chosen, the the LM358, and I only chose that because I've got 100 of them in the drawer. So at some point I will pull that and put something slightly better in that can go slightly closer to its rails. At the moment it's not a huge problem. What it causes is when you have a really low low resistance load, it's really hard to get the really low current values, because this won't go close enough to its rail to get the voltage low enough on the output to succeed. And in fact the voltage clamps at about 4 volts minimum, and it should clamp at 0 volts minimum, but this is only like sort of, you know, point something of a volt error on these guys, unfortunately, because it's yeah, times 6. Everything's so the output is 6 times whatever you've got on here, maybe a bit more than that, maybe 7 times. So yeah, so unfortunately the choice of opamp there, which is what I've got in the drawer, did just limit its operation on those very low current but low impedance loads. So despite the fact that I should swap out a couple of op-amps, I think this has been a pretty successful build, and I've achieved the objectives that I set out, which were to create a variable current source with voltage limit, to sort out all the safety problems, put a switched output on it, and enable presets and things like that to be seen. I'm just going to print up a plastic bracket to mount the PCB onto, and cable tie a few cables and things like that. And next time you see this, I'll be using it as a current source for some nickel plating, and we'll see it being used in anger. So if you've enjoyed the video, please give it a thumbs up, like it, leave comments of course, and if you haven't already done so, go ahead and subscribe. Thank you very much, that really helps. And I'll see you next time. Take care. Bye for now.